Okay, so you might not have realized that when we do our Lewis structures, we are counting the number of valence electrons along the period. And so let's say it's carbon, for instance. So it's 2, 4. And so we're counting 2 in there, and then 1 in there, and 1 in there. Yet we are getting these like tetrahedral, same length things going on. And so how's that possible when you've got these things that are completely different shapes, to have like an S here and an S here and then these two P's, and yet them all be the same length and size and everything else? And so the answer is it's not actually, that's not actually what's going on. These things actually hybridize. So they mix, the waves mix together and form 4 equal waves around the atom. So that is what it looks like here. So that is the CH4 molecule right here. So you've got the S electrons, and what actually happens is they get promoted, which I'm not illustrating but in the slides, but basically you just mix those together and you'll get there's something called a hybrid, which is sp3. And so how do you know it's how many there are? Well, you count them up. So 1s, 1p, so there's 2, and there's 2p's there. So 1 plus 2 is 3, and 1 plus 3 is 4. So there's 4 sp3s, and they are all the same. And so how do you know how many to mix? Well, you'll look at the formula, and you'll count the number of electrode domains. And so maybe there's a lone pair there like NH4 that's coming up on one of these slides. And so 1, 2, 3, 4. So there's 4 domains. There must be 4 hybrid orbitals. And so this one's the number 4. So it'll be sp3. So generally, if there's 2 domains, it's sp. If there's 3 domains, it's sp2. If there's 4 domains, it's sp3. Okay. So let's just look at some examples. So here we have 2 electron domains. So the carbon has sp hybridization, and these ones are not hybridized, they're just p orbitals. So the sigmas are sp hybridization. This guy, we're just looking at the carbon, I think. The oxygen has 3 domains as well. So they're both sp2s, and then the remaining electrons are in the p orbitals to make the pi bonds. There's a nice picture of it there too, by the way. And go so 4 domains, sp3s. Okay. And so let's do a few of these. Okay, so BF2, we can see that has 2 domains, so it must be sp orbitals. So this is what it normally looks like in the ground state. So that gets promoted, and then they combine. So you've got the 2p and the 2s, and then they combine. And then you don't write the number there, you just write sp, and just put 1 electron in either of them. And now they're free to form bonds. So if there was, you could actually have it S's, all right? But some of these, it's going to be S and P, and they'll be different lengths, and that wouldn't make sense. In this case, if there were 2 S's, they would still be of equal length. All right. So this one here, makes a little bit more sense in the fact it has to be hybridized. So you don't have like an S and then 2 S's and then 1 P there, and so this one's longer than this one. You have equal lengths. And so the S gets promoted to a P, and then they hybridize, and so you get rid of the entire lot now, and you've just got something that's an in-between energy level. And so it's sp2, and there's 3 of those, and then now they can form the 3 bonds that are of equal length. All sigma bonds, all right? And so this one's got 4. You don't have 2 short bonds and 2 long bonds. You have something in between, something of an in-between energy level. That gets promoted up there. They combine. You got 4 sp3 orbitals, each with 1 electron in there, ready to form a bond. This one's the ammonia. So this one's the first example where there's not a bond for this electron domain. And so it's the same deal, except you now have actually one of the hybrid orbitals as full, not forming a bond. Okay, so there's a lone pair, and then there's 3 sigma bonds. Now, last one, this is for the oxygen, because this is only going to have sp hybridization and then electrons in 2 pi bonds. So this one's got 3 electron domains, so it's sp2. Well, so that's up to 3. And 2 of them are full this time, and only one of them's free to form the sigma bond. Okay, just because the syllabus says inorganic compounds need to be covered, I guess that's inorganic. I'm just showing you a picture of a complex ion. So that one has like 1, 2, 3, 4, 5, 6. So you need 6 hybridizers. And so 2 plus 1 plus 3 adds up to 6. I don't think you'd ever get asked that. A little bit nasty, but that's how it looks like, okay? Not in your textbooks, and just out of curiosity. All right. So now that you're at the end of this unit and you've done a lot of learning, you can now do a full analysis on molecules. So I've done an SO42 minus. I'm not going to go through this because that would take like an hour lesson. I'll just show you the answer. You could try doing nitrate or carbonate. That would be similar to this. And just to show you the complexity of it, so first of all, I'd get everyone in the class to try and do the Lewis structures to try and get the various options. And it's comforting to know that once you've done the formal charge on all the different variations, so anything that's got resonance, this one's the resonance one because it's got a double bond, will give you a hint that's probably correct because that's what happens with bonds. They all resonate and form and a bit of a mess. That gives you a hint that's going to be the correct one. But when you do the formal charge on it, it also turns out to be the best one as well. So that's comforting to know that that all works, and it breaks the octet rule, which makes sense as well because it's large. So they're all hints that we're on the right track, to be honest. Breaking the octet rule and resonance, and then confirmed by formal charges. So bond, so that's how we draw the resonance structure. Bond order is just something extra. It's kind of nice to know how the bond is. It's 1.5 bonds. It's kind of interesting and helps you understand a little bit better. But that's not your syllabus. So that's so now we know they're 4 equal bonds, and now we know it's for sure. It's definitely tetrahedral 1 and 0.5. So this is the hybridization bit. Now, notice I haven't done oxygen. I'll just do this one first. So we've got 4 sigma bonds, which are here, and then we've got 2 pi bonds, which are resonating. So there's the room for the pi bonds. And this, we've just analyzed the sulfur molecule. And even if we drew that as a tetrahedron, I'm not quite sure. I guess you could draw that as a tetrahedral molecule. Like this, so that's going out of the page, and that's going, into the page, that's going out of the page. God knows how you're going to draw the pi bonds around this 3-dimensional space that are resonating. It's easier when it's like flat, like benzene, you can just do it up below and above, but this is, and make it sort of 2-dimensional, but this one's, wow, really 3-dimensional. And then God knows how you're going to analyze the oxygens because they're resonating. So I haven't analyzed the oxygen. I don't even know if it can be analyzed. So that's it. It's pretty complicated, and this whole process I think would take a whole lesson. So definitely worth doing because you're going to reinforce a heck of a lot of pretty much everything you've learned so far. Definitely Lewis, all the different Lewis combinations and the formal charges and hybridization and bonding and angles and who knows what else. Okay, so have a go with doing that maybe with nitrate or carbonate.